The minimum allowable wire size for a 20 amp branch circuit is 12 American wire gauge, commonly abbreviated as 12 AWG. This is based on the ampacity of the wire, which is the maximum amount of current a conductor can carry continuously without exceeding its temperature rating. The National Electrical Code, abbreviated NEC, provides guidelines for selecting the appropriate wire size for different circuit ampacities. In general, for a 20 amp circuit, a 12 AWG copper wire is the minimum size permitted, assuming standard insulation types and ambient temperatures. However, it's crucial to consider factors that can affect the wire's ampacity and require dirting. Dirting refers to reducing the allowable current carrying capacity of a wire due to certain conditions, such as high ambient temperatures, multiple conductors in a raceway or cable, or specific types of loads. Firstly, high ambient temperatures can significantly impact a wire's ampacity. The NEC provides correction factors to adjust the allowable ampacity based on ambient temperature. For example, if the ambient temperature is higher than 30 degrees Celsius, which is 86 degrees Fahrenheit, the ampacity of the wire must be reduced. These correction factors are found in NEC Table 310.15 bone. Secondly, the number of current carrying conductors in a raceway or cable also affects ampacity. When multiple conductors are bundled together, the heat generated by each conductor can raise the overall temperature within the raceway or cable. The NEC addresses this by requiring adjustment factors to be applied when there are more than 3 current carrying conductors in a raceway or cable. These adjustment factors are found in NEC Table 310.15b3. Thirdly, certain types of loads can also require dirting. For example, if a circuit supplies continuous loads, which are defined as loads that operate for 3 hours or more at a time, the NEC requires the branch circuit conductors to be sized at 125% of the continuous load. This is to account for the sustained heat generated by these loads. The NEC specifies the ampacity requirements in NEC Table 310.16, which provides the allowable ampacities for various wire sizes and insulation types. For example, 12 AWG copper wire with a typical insulation type such as THHN or THWN has an ampacity of 20 amps under normal conditions. However, it is essential to consult the specific ampacity table in the NEC for the appropriate insulation type and temperature rating of the wire being used. To ensure compliance with the NEC, it is important to follow a systematic approach when selecting wire sizes for branch circuits. Firstly, determine the total load in the circuit. This includes all the appliances, lights, and other equipment that will be connected to the circuit. Secondly, determine if there are any continuous loads on the circuit. If there are, the branch circuit conductors must be sized at 125% of the continuous load. Thirdly, determine the ambient temperature in the area where the wires will be installed. If the ambient temperature is higher than 30 degrees Celsius, correction factors must be applied to the allowable ampacity of the wire. Fourthly, determine the number of current carrying conductors in the raceway or cable. If there are more than 3 current carrying conductors, adjustment factors must be applied to the allowable ampacity of the wire. Fifthly, select the appropriate wire size based on the adjusted ampacity. Make sure to select a wire size that has an ampacity equal to or greater than the total load in the circuit. Finally, consult the NEC for any additional requirements or exceptions that may apply to the specific installation. It is important to note that the NEC is a minimum standard, and it may be necessary to use larger wire sizes in certain situations to improve the performance and reliability of the electrical system. For example, using larger wire sizes can reduce voltage drop, which can improve the performance of sensitive electronic equipment. In addition to wire size, it is also important to select the appropriate type of wire for the application. Wires are available with different insulation types, each with its own temperature rating and suitability for different environments. For example, THHN wire is commonly used for dry locations, while THWN wire is suitable for wet locations. It is important to consult the NEC and the wire manufacturer's specifications to select the appropriate type of wire for the application. When installing wires, it is important to follow all applicable codes and regulations. This includes properly supporting and securing the wires, using the correct type of connectors, and ensuring that all connections are tight. Improperly installed wires can create a fire hazard or cause other electrical problems. To further elaborate on the concept of ampacity, it is crucial to understand the factors that influence it. The ampacity of a conductor is primarily determined by its ability to dissipate heat. When current flows through a conductor, it generates heat due to the conductor's resistance. The amount of heat generated is proportional to the square of the current and the resistance of the conductor, as described by Joule's law. If the heat generated exceeds the conductor's ability to dissipate it, the conductor's temperature will rise. Excessive temperature can damage the insulation, reduce the conductor's lifespan, and even create a fire hazard. Therefore, the ampacity of a conductor is limited by its temperature rating, which is the maximum temperature the conductor can withstand without degradation. Several factors affect a conductor's ability to dissipate heat. Firstly, the conductor's material plays a significant role. Copper and aluminum are the most common conductor materials used in electrical wiring. Copper has a higher conductivity than aluminum, meaning it offers less resistance to current flow and generates less heat for the same amount of current. As a result, copper conductors generally have higher ampacities than aluminum conductors of the same size. Secondly, the conductor's size and shape also influence its ampacity. Larger conductors have a greater surface area, which allows them to dissipate heat more effectively. Stranded conductors, which consist of multiple smaller strands of wire twisted together, also have a slightly higher surface area than solid conductors of the same gauge, resulting in a slightly higher ampacity. Thirdly, the type of insulation surrounding the conductor affects its ability to dissipate heat. Different insulation materials have different thermal conductivities, which determine how easily heat can flow through them. Insulation types with higher temperature ratings, such as THHN and XHHW, can withstand high temperatures without degrading, allowing for higher ampacities. Fourthly, the ambient temperature surrounding the conductor also affects its ampacity. Higher ambient temperatures reduce the temperature difference between the conductor and its surroundings, making it more difficult for the conductor to dissipate heat. As a result, the ampacity of a conductor decreases as the ambient temperature increases. Fifthly, the presence of other conductors in close proximity can also affect a conductor's ampacity. When multiple conductors are bundled together in a raceway or cable, the heat generated by each conductor can raise the overall temperature within the raceway or cable, reducing the ampacity of each conductor. The NEC provides adjustment factors to account for this effect, as mentioned earlier. In addition to the factors mentioned above, other considerations can also affect the selection of wire size. For example, voltage drop, which is the reduction in voltage along the length of a conductor, can be a concern in long circuits. Excessive voltage drop can cause equipment to operate inefficiently or even fail. To minimize voltage drop, it may be necessary to use a larger wire size than required by ampacity considerations alone. The NEC provides guidelines for calculating voltage drop and recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. Furthermore, the type of load being served by the circuit can also influence the selection of wire size. For example, circuits that supply motors or other inductive loads may require larger wire sizes to accommodate the inrush current that occurs when the motor starts. The NEC provides specific rules for sizing conductors for motor circuits. It is essential to consult the NEC and other relevant standards to ensure that the wire size selected is appropriate for the specific application. In summary, selecting the appropriate wire size for a 20 amp branch circuit requires careful consideration of several factors, including ampacity, ambient temperature, the number of conductors in a raceway or cable, the type of load being served, and voltage drop. While 12 AWG copper wire is generally the minimum size permitted for a 20 amp circuit, it is crucial to consult the NEC and other relevant standards to ensure that all applicable requirements are met. Always prioritize safety and compliance when working with electrical wiring.